So it's my pleasure to introduce Zhang. Zhang, can you hear us?
Yeah.
The floor is yours. Thank you.
Okay, great. So thank you everyone for coming to the talk. Yeah, sorry cannot be there. There's some last minute visa issue, but today I'm very excited to share with you something that we have been working on recently about distributed learning, and also if we have time about more on the data perspective. So I think everyone here just witnessed this amazing progress of machine learning and AI in the last essentially decade, right? So I mean, if you look at what happened last year, it's just really fascinating. So there's an image model like Stable Diffusion. There's the NLP model like ChatGPT, right? So it's really make this huge difference about the model quality, and it's not really kind of happen in an unexpected way, because you can really kind of track the quantitatively the quality of the model progress in the last decade, right? If you look at the ImageNet, if you look at like Squad for NLP, you see in the last like 6 years to 10 years, this like 20 to 30 points improvement coming from the model quality. So and because of that, it start to bring the model quality from like low 70s to like high 90s, start to actually make this kind of qualitative difference that bring all the techniques into our daily life. So, but of course, there are so many things that actually come together to actually make all this happen. And among them, I think there are two fundamental forces that have been keep pushing us forward. So, and they're the data and also the compute. There are kind of different ways for you to look at these two different angles. But one of the way is from this paper from OpenAI a couple of years ago. That is scaling law, right? If you look at what happened on the left-hand side, right, so more data you put into the system, the better the model that you are going to get. But of course, right, the data is not free. The more data you push into the system, the more compute you are going to burn, and the more compute you burn, the better the model you are going to get. And because of the phenomenon that look like this, if you look back in the last like 10 to 20 years about what data set people are having in the community, we actually went a really long way, right? We essentially start all the way from 10 years ago. I think the biggest data set is like 1.3 million images, all the way to today, people putting billions of those images into the training process. And of course, the compute side start also to explode, right? If you want to do a GPT-3 style model, you are talking about a couple thousand GPU running nonstop for a couple months, right? And that doesn't even give you the most expensive model that you can actually train today. So as a community, we have been making essentially really huge effort on data and compute, but there are also challenges that I think we are facing today. So I think the challenge of today is really like, even though we know how to build those machine learning applications at today's scale, actually building them can be just ridiculously expensive, both on the data and also on the compute. It's very easy to essentially drag you into this $1 million region. And what's even more fundamental is that if you want to scale the whole thing by another 10 times, so doing that is actually getting way harder. So simply because there are actually multiple bottlenecks that we are facing, and they become even more critical when you actually scale even more. So there are two bottlenecks I think we are very excited about. The first one is about communication and data movement, right? So because training anything at scale is just super expensive on the communication side. So just to put some number onto it, if you want to do a like 6 billion parameter model training for like 300 billion tokens, this is like GPT-3 recipe. If you have like 32 machines, every single one have like 4 GPU. So we are talking about like during the whole training process, like every single machine going to send and receive like 4 petabytes of data to each other. So if you have like reasonable network like 100 gigabits, it's essentially going to take like 100 hours nonstop just for communication. So if you have a slightly slower network, like 10 gigabits network, so we are talking about this is a workload that's going to take like 1,000 hours to just communicate, but compute only take like 200 hours. And if you want to do something even larger, right? So it's become even more communication intensive. The consequence of this is that if you look at model training today, we are actually largely restricted to like centralized data centers with very fast network connections. It's very hard to use like cheaper alternatives like tier 2 to tier 4 cloud, spot instance, volunteer compute to do like this large scale model training today. And if you look into the future, if you want to say, okay, let's scale the whole thing by another 10 times. So it's even for data center settings become challenging because you start to build this like equally fast or if not faster connection between essentially 10 times more machines. It essentially gets really, really expensive even for data center setting. So the second bottleneck is about data quality, right? Because when you burn more and more compute, you are actually using more and more data, and alongside the increase of data volume, it comes the decrease of data quality. You can see that by just, for example, just query doctor in Lion 5B, right? So you can see, I mean, this is essentially all the doctors. And you can see a whole bunch of data quality issues, right? For example, like these two pictures doesn't really have doctor in it. If you train a machine learning model using those data, I mean, at some point, it's going to associate the wrong feature with this concept of doctor. And what's even more seriously, I would argue, is there's a very clear gender bias coming out of this data set, right? So, and all those noise in the data and the bias in the data are just being reflected in the code of the model. And you can see them in many of the open model and closed model that we have today. So if you want to scale this by another 10 times, right? So as a community, we really in a desperate need to derive this high quality core for data and provide rigorous data quality control for our model training process. So as a research group, the way that we think about kind of all those bottlenecks and the challenges and opportunities is by thinking about this as the tension between essentially three different players. On one hand, you have your data, right? So data start get larger, get more complex. The quality of data start to decrease. The amount of cost you need to actually clean the data, to acquire new data, start to increase. As a consequence of that, the model become larger, become more complex, and both the data and the model is essentially adding pressure to our infrastructure. You start to need a huge amount of kind of floating point operations and storage to do inference, to do training. And as a reaction to that, the infrastructure start to evolve in essentially two different ways. It start to specialize. That's why we see those like specialized hardware or tensor core, right? So essentially they drive this like current AI trend, and infrastructure start to scale out, right? You start to have hundreds of thousands of those like unit of compute to do a single training process altogether. So when you kind of break the tension in different ways, when you get all of those things right, amazing things can happen, right? So one of the example is essentially this Llama moment a couple of months ago, right? So if you look at the first version of Llama, it is essentially 1.4 trillion tokens, and it burned over like 1 million GPU hours. And when you get the data and the compute in the right way, amazing model that actually happened. So as a research group, the thing that we are really curious about is by looking at the tension between the three different players and try to understand, okay, how can we break the tension from the infrastructure side, and how can we break the tension actually on the data side? So, and on the infrastructure side, that's really closely related to what we are talking about today in the workshop. That is essentially how can we deal with distributed learning at large scale. So on the infrastructure side, the working hypothesis that we have, so first I have no idea like about whether those are correct or not, but these are two hypotheses that we have when we thinking about the problem. The first working hypothesis is within a computer, there will be a continual trend of aggregation just because of the memory system. So if you look at the computer like today, actually not today, it's like a couple years ago. So if you look at it like this memory hierarchy coming from like A100 GPU, right? So you have this like SRAM, you have like HBM in the GPU side, and then you have your CPU memory, and CPU and GPU connect with, for example, PCIe, like 20 gigabytes, something like that. So I mean, it's kind of a little bit disaggregated in the way that CPU and the GPU, you think about them as kind of different compute unit. But if you look at what happened today and probably imagine what happened in the future, is probably all those like computer unit, at least our working hypothesis, is going to be continued to be aggregated, right? So that's already happening, right? If you look at Grace Hopper, so what happens is this like it's really amazing, like 900 gigabytes per second, this like connection between like GPU and CPU, right? So when you have something like that, right? So how we think about memory hierarchy, how we think about distributed learning within a machine start to change, right? That's already happened. For example, if you have a kind of so M2 Ultra on your MacBook, right? So in the middle, the memory system is connecting CPU and GPU by like 900 gigabytes per second, right? So I think this trend also continue going to happen, right? There will be this continued aggregation within a box. On the other hand, the second hypothesis that we have is you will see this continued disaggregation essentially across different data centers. So compute will be scattered. And this is actually something that kind of I learned recently. So I actually didn't think about why it's going to be disaggregated, but one of the reasons is because of power, right? So for example, this is the power sources in Germany, right? So every single dot is essentially the power source, right? If you look at like the dot in the middle, it's a pretty big one, right? So that the whole power plant is kind of can only power like 1,800,000, like GPUs. And if you look at how many GPU we are having, NVIDIA essentially shipped like 500,000 just last year, right? So, and because and this is assuming we are using the whole power plant to do nothing but only power the compute, right? So, and because of that, I think naturally there will be this disaggregation of compute that be closer to the power source. And within each of those compute unit, there's this interesting aggregation happen, right? So this is essentially our working hypothesis when thinking about infrastructure. And because of this, one thing that we have been doing that we are very excited about is really trying to optimize distributed and decentralized infrastructure, because we cannot believe there's a fundamental reason that this aggregation will happen at the infrastructure level. So we better prepare for that. So in that case, essentially, one of the motivation to be a little bit more concrete is for many of the things that we complain we don't have compute, we actually do have compute. And the only problem is today they are scattered, and we believe in the future they are continually going to be scattered. So just like some more numbers, right? If you want to do a GPT-3 model, the biggest one, like 175 billion parameter, right? So this is how many floating point operations that you need. So it kind of looks like a lot until you realize I'm just floating at home project where everyone contributes their GPU to fold the protein. They can harvest essentially the same amount of compute in just less than 2 days. So the compute is there, right? So if the community say, okay, let's just build an open model at the GPT-3 scale, I would argue that we do have the compute. But what's actually stopping us from doing that is this gap between essentially on the left-hand side, right? You have this very beefy data center where you train this model. On the right-hand side, when you think about this volunteer compute paradigm, you have machines being connected by, like, for example, 100 megabase network. So there's this like 3 orders of magnitude communication gap we need to fix. And then there's this like vast heterogeneity of devices and networks that we need to handle. But once we fill this gap, right? So I will argue the availability of compute is not really what's stopping us. It's really the communication between them that's actually the bottleneck. So it's not only a bottleneck for decentralized and disaggregated setting, it's even a bottleneck inside data center, right? So this is one of the training runs that we have been running last year in one of the kind of most powerful supercomputer in the world. So as you can see on the kind of x-axis, when you reach like 3,000 GPUs for the single run, you start to see this gap between ideal scaling, which is the green curve, and also what you are actually getting out of the system as throughput, which is the blue curve. It doesn't look like a big gap until you realize this gap actually means like 500 GPU are just essentially idle during the whole process. Essentially, 500 out of 3,000 GPU are just like doing nothing because of communication. And of course, the thing that on the kind of right-hand side, you have the central network, but there's things in the middle, for example, multi-cloud, spot instance, serverless environment, they don't have control on the locality between communication and computation, right? So our view is like the more you can move things from the left-hand side to the right-hand side, you start to open up more choices for the user, and potentially the whole thing will become cheaper. So that's essentially have been our journey, essentially try to optimize the communications to make sure we can move more and more workload to the right-hand side. So at a high level about what we learned over the years is, so we want to train a neural network, right? So, and there's a whole bunch of layers, right? So, and there's a loss layer at the end, and you have your training data, you draw a sample of the training data, and you can do essentially 2 things. You can just like do a forward pass, compute the loss, and then you can do a backward pass, essentially you compute the gradient for every single layer. But of course, right, we want to do data parallel, you have multiple of those, right, doing this in parallel. And then when the network is actually too large, doesn't fit into a single machine, you start to actually partition them onto different machines. So once you take this view, you can see, okay, in this diagram, there are actually 3 different communication channels. You need to communicate during forward pass, which is your forward activation. you need to communicate during the backward pass, which will send back the gradient, and then you need to communicate for this like data parallel training to communicate the gradient of every single layer. So one thing that we learned over the years is essentially all those channels can be compressed in a very aggressive way without hurting the model quality. So of course, they need different algorithms that we will see later, but there exists a single algorithm under which you can compress all the channels very aggressively, but statistically you get the same model in the end. So we can look at different channels kind of one by one. So for example, like looking at the data parallel channel, I think the community understands this really well in the last 10 years. So the mathematical problem that we are trying to deal with, essentially we want to minimize the expectation over data. So that's essentially what we are trying to do. So because we are building systems, let's put some constant onto it, right? So this is the data, right? You are taking expectation over it. If you are doing like 300 billion tokens, yeah, probably like 1 or 2 terabyte. That is how large that variable actually is. X is the model, right? And then the F is the computation function for the loss, right? So depending on what model you are trying to do, probably like half a teraflops per token, right? And you want to do like 300 billion tokens during the whole training run at least. Right? So how can we do this? The baseline algorithm, I think everyone knows about it, is like essentially data parallel SGD, right? Essentially, you have every single machine hold a model replica, and you keep doing these 4 steps again. You synchronize your model, you get your local data, compute local gradient, and then you update your local model. You keep doing all of this like millions of times, essentially you get a model in the end. So it turns out there are actually many things you can actually play with when actually implement that algorithm, right? You can use different communication channels. You can do lossless communication, specification, and quantization, and you can have different communication patterns, right? You can have the centralized view where everyone talk to each other. You can have this asynchronous pattern. You have this decentralized pattern where you have like no single kind of central server, but every single one just essentially have this like gossip style communication, and you can actually put them together. You can have a decentralized, asynchronous, sparsified communication pattern, right? So we have been playing with different combination of all of this. It turns out for all the combinations, you can actually have some algorithm that give you a pretty good convergence behavior. So that's actually one thing that we learned over the years. So, but recently we start to look at this and think, okay, so how far can we actually push for it? So can we compress communication by like 100 times? So that's actually the routine that interesting things start to happen when you really try to push the communication ratio to like 100 times for data parallel training. And because that's kind of reaching the limit of what a single method in the previous slide can actually do. So just look at some of the example, right? For example, if you say, okay, so I have like D numbers, right? So one thing I can do is like, okay, so let's just sparsify it. So the moment you sparsify it, you kind of decrease the amount of value you need to encode. But on the other hand, one additional piece of information to communicate is essentially the sparsity pattern. Right? You kind of need to encode the indices in some way. You can use a bitmap. You can have a list of integers to store it. But essentially, this is actually what's going to happen, right? The x-axis is the sparsity. The y-axis is essentially the communication ratio. So as you can see, if you say, okay, I want to do like 100 time compression, actually 1% of sparsity is actually not enough because you need to send both the value and the indices. So essentially, we are talking about if you want to compress your communication by 100 times, you probably need to enforce a 0.3% sparsity. And often the case, a little bit too much for the algorithm to converge in a stable way. But you can combine things together, right? So this is when you reach the limit of a single method, but you can start to combine stuff. So for example, you can say, okay, like I can do top K, but I can also do a quantization step, right? So I can just compress my value into qubits, right? In this case, I decrease the value, my index is still the same. So what's interesting is when you actually combine these two, you get essentially even more aggressive communication out of it. But the problem is that if you're not being careful about how you combine this, you kind of quickly reach this like diminishing return region, right? So here, if you combine top K and quantization, you can see that the x-axis is how much you quantize, but even though you can quantize the whole thing in a very aggressive way, you are actually not getting too much out of the system side, right? So but you can combine even more, right? So that's actually where the whole thing become interesting. So one thing you could do is, okay, so let's combine another method, right? So let's do a like random sample, right? Like just randomly kind of throw out values. I do a random sample, and within the sample, I do a top K, and then I do a quantization, right? So this actually give you something that's very interesting, that start to give you a kind of a compression method that can give you like 1% sparsity, 4-bit precision for every single value. But on the other hand, have this like 100 times like compression ratio coming out of the system side. So, and here's one algorithm that we have. It's kind of very interesting, right? So we call the whole thing like cocktail SGD because it really have a mixture of compression method. So how the whole thing works, right? So essentially, like every single machine just do their local iteration, and we try to essentially fit communication into the slot, right? So come up with a global state, do a local aggregation, right? The goal is really to have communication that fully fill the slot, that do not slow down the computation. So what's interesting is actually the kind of the compression, kind of communication side, right? So what we do is, if you look at this global state, so first one, it has a single step stillness, right? Because we are doing communication, you are also doing computation. So what we do is we randomly pick like P% of parameter to communicate, and for that P%, we do a top K, right, to keep the most significant value, and then we do a quantization of the value. After you do these 3 different steps, you do a global communication, right, to compute the sum. So the high-level idea is you kind of really need to compose different methods together to actually get something working. So it actually have a like open up a pretty interesting trade-off. So if you think about this, right? So both top K and random sample, they will introduce essentially sparsity, right? So and value quantization will just decrease the storage need for the value. But there's an interesting trade-off in the sense that if you think about how K is top K and P is essentially random sample. So what's interesting is, at least in the convergence upper bound perspective, you see this very robust aggregation between K and P, right? Which probably means that as long as your random sample rate is not too small, it won't have influence on the convergence beyond what top K can give you. So essentially, it's possible to actually strike a very good balance between convergence, which is on the machine learning side, and the compression ratio, which is on the system side. So that's actually the fundamental reason that this thing actually works pretty well. So like these are 2 different examples where the kind of left-hand side is instruction tuning 6 billion parameter model, right-hand side is a 20 billion parameter model. So you see the green curve is actually cocktail SGD compressed to like 100 times. And the blue curve is essentially all reduced. You can see they are pretty much kind of converging to the same thing. If you just put this 100 times on a single method like local SGD, or just only doing top K, you start to see this gap, right, between a single method convergence and what you could have out of the full precision convergence. And what's even more interesting is on the system side, right? Because you are compressing the whole thing by 100 times, even though you could have, for example, like 1 gigabit network, essentially you are getting the same throughput as if you are in the biggest data center in the world. And what this actually means is large scale data parallel training for like billion level parameter models is actually possible over 1 gigabit network. So that actually makes us like really excited. So, and there are more channels, right? So if you look at the forward activation channel, it's actually very interesting, right? So for this channel, you kind of need to have a different algorithm to actually deal with that. So here, the mathematical problem that we are trying to solve essentially start to change, right? So instead of have a single function, which is the whole neural network, you start to have, let's say, okay, we cut the neural network into 2 different cuts. And then during the forward pass, you are sending the value of G to F, right? So, and to just put some number onto it, If you are doing a GPT-3 style model, essentially every single 1,000 token you have, you are sending like essentially 24 megabyte from G to F, right? So it's kind of quite significant. So we kind of have to do something about that. So, but this is actually very hard, right? So we kind of don't have a good answer to this problem in general, but we are making some progress. Really excited to share and get feedback. So the fundamental reason that this problem is very hard is both F and G, they are actually black box functions that we cannot open, and because of that, the bias coming from G is very hard for you to do like error compensation because you don't really have a strong structure of F, right? Very different from gradient. Gradient have this inherently linear structure. You can do error compensation. You can do a whole bunch of things to actually fix the error. You can delay the error to the next round. But for activation compression, it's actually very hard. It is kind of very hard for you to keep track of the error of F and compensate that in the next iteration. So we don't really know what to do. But there are some cases that we have some idea what to do. So for example, if you allow me to do multiple epochs, right, which means that for the same example, I'm going to see that multiple times. So in that case, we do know what to do, right? So essentially, the first time you see the same example, right, so you are going to do a forward pass with a model, and then the second time you see the same example in the second epoch, you are going to do a forward pass but with a different model. So because all of these are coming from the same example, once you could do is essentially you could just like compute the difference of activation across different epochs, and instead of sending the activation directly, you are sending the difference, and then you can compress the difference in a pretty aggressive way. So the reason that it works is that essentially the more the model converge, the longer you train, the model will converge better. And what that means is if you look at the change of the model across different epochs for the same example, it becomes smaller. And essentially the change of activation of the same example will become smaller. And using the same amount of bit, the quantization error, because the diff becomes smaller, the quantization error also becomes smaller. And then as long as you have a precision level that's high enough that you can actually close this loop, so you are going to have an unbiased convergence out of this. And this is something you can write down kind of precisely, right? So here, like you have one condition, which is the red part, essentially tell you, oh, this is actually the minimum amount of precision I need in the compression thing. But once you have that, you start to only introduce this additional term in the convergence. So we are kind of very excited about this because, like, to our best knowledge, is one of the first unbiased convergence result for activation compression that doesn't assume the nonlinear function do not introduce bias, right? So we're kind of really excited about this. But again, this is only for a very, very restrictive setting, right? We don't really know how to do anything just beyond this. So, but what was even more interesting is now you can compress all the channels, you can start to do kind of interesting stuff, right? So here's one example that we start to cut the model into 8 different pieces. And then we do a 3-bit forward, 6-bit backward, and 4-bit data parallel gradient compression. And as you can see, the green curve is essentially the convergence with compression. The blue curve is essentially the full precision communication, right? So even though you are compressing the whole thing in a very aggressive way, you are essentially getting the same convergence out of it. So what's even more interesting is because now we kind of compress aggressively, we say, okay, so let's actually have 8 machines, so across the world, and put that 8 different pieces onto different machines, right? You are actually doing like geo-distributed model parallel and data parallel. So in this case, even though you are actually having, for example, so here what we measure is like communication like 0.4 gigabits to like 1 gigabits communication between those sites. So in that setting, right, even though you can have a very slow connection between those, you are essentially getting like at most like 1.5 times slowdown coming out of the system from a throughput perspective. And what that means is if you can make your infrastructure, like decentralized infrastructure, like 1.5 times cheaper than the centralized infrastructure, it actually make economic sense for you to do decentralized training. It's actually going to give you something that's actually cheaper than the centralized thing. So decentralization do not need to be a compromise. It doesn't need to be something that you have to do because you cannot do centralized training. So if you can make decentralized infrastructure slightly cheaper than the centralized one, we might be moving toward into a world that we might choose to use decentralized things because it's actually cheaper to do, but it gives you the model of the same quality. So that's why we are kind of really, really excited about this. So, so this is actually some of the work that we have been doing on the infrastructure side. To keep looking at the communication bottleneck and try to understand how can we kind of compress it. We have a lot of fun on the theory, a lot of fun on the system side. So in the last part of the talk, right? So I really want to share some of the things we have been doing, essentially on the data part, because that is really important in the sense that that's going to essentially give us the thing that we train on, right? So one thing that we are trying to do, like is a project called RedPajama. Like the goal is really try to create open data and the framework for data quality to actually achieve like Llama quality and beyond, right? So the first version of the data set is actually, we say essentially, okay, so let's just take Llama 1, which is like a great model, and they kind of describe what they have done in the paper, but don't have the data open. So let's just reproduce it. So, and then the data essentially like 7 pieces, right, with like 1.2 trillion tokens. We try to mimic the distribution of Llama just as close as possible, right? So, and we are really happy to see how much impact that this data set is making in today's open model, right? So there are actually a lot of open models have at least like half of the slices coming out of RedPajama. And we also train our like own models, right? So like we train the base model with like 1 trillion tokens. We start from the PTA architecture, like have a 3 billion model, 7 billion model, and all the instruction tuning. So for pre-training, it's all like full precision communication. But for everything like instruction tuning, the chat tuning, we also build a moderation model. They are all built with a 1 gigabit kind of essentially, like it kind of built with a communication compression ratio that allow you to do 1 gigabit like communication, between those machines without seeing any slowdown. So it's actually have a kind of pretty interesting kind of like model artifact, right? The 3 billion model, because it's so small, you can just put it everywhere, right? So like so Tianqi like put just essentially like using his MLC framework, try to put that on an iPhone, right? We have a lot of fun. It's very easy to run on using Llama CVP because of how small it is. And another interesting is once you kind of instruct tuning it, right? The 3 billion model can be really powerful, right? You can get something that well, it's not a fair comparison in the sense that it's like instruction tuned model, but you can essentially kind of match the base model of some of the 7B, right? So there's a huge potential coming out of small model. So we're kind of really excited about that. And second thing is because the data is open, you can do really kind of rigorous contamination analysis, right? So this is one of the, I think, not one of the first, because I think people from Illusion are doing this amazing work about decontamination, but this is one of the kind of more recent effort that to have decontamination analysis coming from the model side, right? You can actually look at the data and just audit whether we train on the test side or not, right? So that's one of the power of the open data, in our opinion. So one thing that we have been doing in the last couple of weeks is to have the second version of RedPajama, which become a little bit more interesting, right? So it is like 30 trillion tokens, but what's even more interesting is it gave us this modular view of data quality. So we kind of start to integrate what we learned from the first version of RedPajama and think about how can we create an artifact that is useful for the community. So it has 5 languages, 30 trillion tokens. We essentially process all the common crawl dumps, right? And they are available, and you don't have to do that again, like if you want to do common crawl. So, and what's more interesting is we overlay this raw data, the 30 trillion tokens, with essentially 40 different quality annotations. So they actually measure different perspective of data quality for every single document in Common Crawl. So, and the high-level idea is it gives you this way to modularly kind of filter your data and deduplicate your data, right? For example, if you're saying, okay, maybe golfer is a good rule to filter my data, you can actually take RedPajama v2 and write this whole bunch of filters, right? So probably like 100 lines of Python, you can have your best effort reproduction of the golfer data set, right? So if you say, oh, RedPajama v1 is good, if you say, oh, C4 is good, right? So all those signals are enough for you to write like 100 lines of Python script to try to reproduce all those data or state-of-the-art data set, at least in best effort. So, and what's actually even more interesting is, in principle, it gives you this way to actually combine all those quality rules into something better than any of today's open data set, right? We have no idea how to do it, but this potential is actually getting us like super excited. Yeah. So in the last part of the talk, kind of want to tell you a little bit about things we are struggling about that we have no idea how to do. Yeah. So I think evaluation is something we really don't know what to do. Right. Evaluation is a very big problem. So, and this is one of the example, right? So like Hugging Face have this amazing leaderboard for language model, and they have this data set called MLU, right? So it's used to be the case, right? So that the number look like thing on the left-hand side, but around June, there's one researcher who say, oh, actually, if you run this official MLU, you actually get a different number, like very different number. The order of all those kind of models on that data set simply because a very small change on the data start to change really dramatically your perception on the quality. And this is just one of the example, right? So what this really opens up is like how should we evaluate and compare language model in a robust way? Maybe human evaluation is a key, but how can we scale it? How can we make sure it is reproducible and unbiased? So maybe this is one thing that being distributed and decentralized makes sense, right? So the execution is easy, but maybe this decentralized view can help us to come up with a standard about what is a good model, but even that is kind of really hard. So data quality is a big problem, right? So if you look at RedPajama v1, right, we have all those 7 slices, but how can you assign a weight for every single slice? How can you do data mixture analysis? How should we think about data deduplication, right, and how much, right? So after we have the RedPajama data, there's a company called Cerebus have this amazing work called SlimPajama, essentially do very aggressive deduplication from RedPajama and shows on many tasks it actually works better. But how much should we do that? How can we think about data transformation, data debias, data detoxic, right? So all those things, I don't think there's a principal framework for coming to actually handle that, but we actually really need them. So one thing that we hope to actually enable using the RedPajama data is, if you think about what RedPajama actually gives you, it actually says, okay, so we have this one Common Crawl dump, but here are just like 40 different ways for you to measure quality. So here are all the histogram for every single signal, right? So how can we just use those signals to turn these 30 trillion tokens into like 10 trillion high quality core of the data that you can train the next generation of machine learning models? How to do it, and how to do it systematically that you can reproduce on another domain. I think it's really the problem that the community should figure out in the next few years. I think going to have really big impact on how we think about those models. And also, we talk about communication compression. We have been playing with that for a long time, but one thing that we haven't played with is how to do pre-training over 1 gigabit network. Can we put the whole pre-training process over a geo-distributed, slow 1 gigabit network? So together, we have been instruction tuned a whole bunch of models. Every single model we instruction tune, at least most of them, they are actually using the Kotlin SGD algorithm that you can compress. It works really well, but we haven't figured out how to do pre-training. So there are a lot of details to figure out, and it have a different kind of risk portfolio, because how expensive it is, how to control the risk, how to control the regret is something that we don't really know what to do, right? And how does this interact with architectural design? Can we have a model architecture that's simply easier to compress during pre-training, right? So one thing that's very exciting is like DeepMind have this paper that like couple weeks ago. It's really cool. It's one of the first work that I see that actually do communication compression for pre-training, right? So I think that's really open up a really amazing topic for the community to really understand. If you can pre-train a language model in a geo-distributed way, that's going to open up a whole bunch of things. So yeah, so that's essentially all I have. Yeah, thank you so much for your attention. I think I bring us on time. Yeah. So and yeah, I'm happy to answer all the questions and all the feedback you have. Yeah, thank you. Oh, by the way, we have this platform called Together. Play with it and give us feedback. Yeah. Thank you.